So in the second video, we're going to talk about the Geographic Coordinate System, or GCS as we sometimes call it, and how do we start using this and what are some of the issues that need to be taken into account. So there might be some of you who believe in the Flat Earth organization or the society. However, the Earth is actually what some people will call a lumpy potato. So it's not a sphere, it's not a perfectly round thing, and it's definitely not flat. It is something in between. And you're going to hear terms like geoid, ellipsoid, and different concepts of how we represent this complex system or this complex surface or sphere in our systems. And this is why, if you look at that map, you'll see that there's a distortion in the map, not the map, the lumpy potato, if you would like to call it that, in that it's not perfect. And that's why we need to use different representations of the Earth and the shape of the Earth in different parts of the world. And this is the premise of this discussion on using the ellipsoid, or what definition of the world surface we're using, plus a datum to localize it. So in South Africa, up until 1999, we used to use a representation called the Modified Clark 1880. And this had been localized in Buffels Neck in the Eastern Cape in East London. And this is where they had taken this Modified Clark 1880 spheroid and placed it on the South African surface. And we did all our measurements from a datum point of view from this origin. So in those small brackets in the italics, I've used the European Petroleum Standards body codes for the datums, if you were wondering what that is. So if you ever go and do a search, that will come back to the Cape datum. In 1999, it was decided to adopt a new datum in South Africa using some of the newer datum representations or spheroid representations that had been created. So with the advent of space travel and GPSs and being able to measure the Earth in a better way, it became easier to get a better approximation of the shape of the Earth and start implementing that. And that's that WGS 84 spheroid. And that is now a newer version of what the world should look like. We decided to use the epoch of 1994, so the representation of 1994, and that's why it's called Hartebeeshoek. Hartebeeshoek because at the Radio Astronomy Telescope at Hartebeeshoek, just outside of Krugersdorp, they have placed the origin of the datum on the telescope. So that is why it's called Hartebeeshoek. We use WGS and we use the Hartebeeshoek datum. And this is the official datum that has to be used in South Africa at this point in time. And I'll discuss the issues why we don't use at certain scales WGS, but we'll touch on that just now. I was recently involved in a project looking at datum definitions in South America, and we needed to make sure that the software could handle them. And it opened up a very interesting set of discussions. They have a datum called Surgas, and Surgas was updated in 2021 from the 2016 datum. And you start asking the question of, well, but that is quite quick. It's been 5 years. Why are you updating your datum? And Chile is moving between 2 and 4 centimeters a year. So they have to keep up with the movement of the continent. There was an earthquake recently that shifted a large part of South America with between 1 and 2 meters on the Earth's surface. So they have a highly dynamic environment in South America, which has to be accommodated and with changing datums and changing spheroids. We are not like that in South Africa or Southern Africa, but still, this is why we keep on changing and updating these spheroid and datum definitions. So what is the difference between Cape and Hartebeeshoek? Well, about 300 meters in north and 50 meters in east. And this is just something that has to be accommodated and taken into account when we start capturing data. So if all your data is in one datum, i.e. Cape, it's fine. But if you've got data in Cape, but you're now capturing data in Hartebeeshoek, now you have to start taking that into account, because the data will actually not match. And you'll have to start looking at transformations to start looking at that. So datums are going to continue to be updated based on newer technologies and approaches to estimating the Earth's surface or estimating the Earth. But in the case of places like Chile, it's ongoing because they live in such a highly dynamic area on the Pacific Rim. So we use multiple transformation methods, and I'm only going to touch on two of them. The one is this 4-parameter Helmholtz transformation, and then we'll look at what's called the NTV2, or National Transformation Version 2 grid. And I just want to bring this to your attention of some of the issues here. Datum transformations have two clear reasons why we have to use them. The one is we're revising the shape of the Earth. So we're starting to understand it better. We're using different models. We're coming up with different approaches. However, the other side is between Clark 1880 and Hardeber's-Hoek, we needed to fix some of the issues in the geodetic network. And what I mean by that, if you go back in time, people used to measure the trick beacons on top of mountains using some very old technology and literally chains where they would have different lengths of chains, and they would measure the lengths of the chains. And if you go into the details, the difference between measuring it in the middle of winter and measuring in the middle of summer, when the heat differences will make the chain different lengths, there were a lot of things that needed to be taken into account. And some of the trick beacons are not 100% in the right place. So the coordinates that we had for them were measured, but were maybe out by half a meter, maybe out by a meter. That doesn't sound like a lot, but when we're basing all our systems onto those trick beacons, it could be problematic. So one of the things that we need to do with these datum transformations is not just fix the shape of the Earth, but take into account things like these inherent errors in the geodetic network. And this has all come of age with concepts such as GNSS or GPS, where we now can use a system that works autonomously or without taking into account the issues of the Earth's surface, etc., and trick beacons and things. So the one approach is, and this we use when we do on-the-fly projections, the ArcGIS technology does this, is it takes the Cape datum, it takes the WGS Cape datum, it takes the Hardeber's-Hoek datum, and we use a transformation called Cape to Hardeber's-Hoek, and you'll see it does a movement in X, Y, and Z, and it's about 0.14 of a meter, so 14 centimeters accuracy. Now that might be perfectly good enough for your application, but in the surveying sense, it's not, and we have to use a different transformation matrix. And here we use that thing called the NTV2 grid. And this is a more complicated process, it's a more rigorous process. And it takes into account both the datum changes in those top paragraph and the errors in the geodetic network. And here you'll see we're down at 0.01 of a meter, so 1.6 centimeters. So it all depends on what you're trying to do. Are you managing cadastre, or are you managing a wetland definition? But please look into this, make sure you understand the implications of this, understand the origin of your data. So one of the things that you can do, you could take data that's been captured with a GPS. So it did not use the old trick beacons. You need to understand if that's the case versus data that has been captured using the trick beacons, because the approaches to do the transformation will be different in both. And make sure you understand these, make sure you have a good understanding of what's going on and where the data comes from, because that will assist you in picking the right process and the right approach. Up to now, we've been talking about horizontal datum, so actually your X and Y. But we also have the concept of the vertical datum, and that is now the height of the Earth's surface, or this geoid as we speak about, so the geoid, ellipsoid, and then the actual Earth itself. And GPS technology or GNSS coordinates do not measure above mean sea level. They measure above the ellipsoid height. So if you are starting to do things where the height value is critical, very important, you need to use something called the geoid separation, which gives you the difference between the actual height and the ellipsoid height. And for a lot of applications, this is not crucial, but keep this in mind that one has to understand this. Mean sea level is an interesting concept. Mean sea level in Greenland is totally different to the mean sea level somewhere on the equator, in excess of 50 meters. So the term mean sea level is not actually a correct term. It's not mean across the whole world. It's not an average across the whole world. And why is that? The Earth is spinning and the water gets pulled towards the equator. And therefore, there's less water on the poles and more at the equator. And that's just something that if you have to get into this concept of sea level mapping and mapping of low water marks or high water marks, it's something to take into account. A lot of us, it's not that important, but for some of you, it might be something that you need to make sure you know some more about. Chief Directorate National Geospatial Information have published a thing called the SA Geoid 10, a 10 centimeter gridded geoid, and that comes from a gravimetric model. So they've looked at the gravity constants across South Africa, and they have worked out a model, and there you can see that it does vary. The darker blue is showing that there's a slightly different model that needs to be applied to the lighter areas. And once again, make sure you're aware of this. Make sure that when something happens and you're looking at data coming from a LiDAR sensor and it doesn't seem to want to fit, what vertical datum are you using? How are you approaching that? So what's the take-home message here? Well, the Earth is not round. It is there, and there are many approximations or versions of the Earth. So we talk about Clock 1880 as one. We talk about WGS. There are multiple versions of the Earth's. And depending on where you are on the Earth, what you're trying to map, what area you're mapping in, you need to take this into account. This measurement is improving over time. So potentially we might get a Hartebeest Hoek 2020 or a Hartebeest Hoek 2050 in the future. So it's not something that's just a once-off. It's something that we need to keep taking into account. Next, what are these projection properties? So we talk about projections, but what are the properties of a projection? Now, if we look at the left, it talks about the geographic coordinate system, and that's defining a position on a round surface, so the 3D surface of the world, and we measure everything in degrees. So how do you measure a distance in degrees? Or how do you measure an area in degrees? And keep in mind what I said earlier, the longitude value at the equator is 111 kilometers versus the longitude value at the pole is 0 kilometers. So we do not have a unique measurement. So this is where projections start coming in. If we look at the right, we define a projection on a 2D model of the world. So that now makes it a flat plane or a map. And here we can measure lengths, angles, distances, etc. And they all measured in a standardized measurement, such as meters or square meters or degrees, etc. So that is why we have to move towards projections and can't keep everything in a geographic coordinate system, because what we measure in the south of South Africa versus what we measure on the equator is different and is not consistent. But let's look at the history of projection. Projections have a checkered history because it all depended on what your rationale was to have the projection in the first place. So, was it a political? Did you want to make your country look bigger? Did you want to make your country look like it was bigger than your neighbors? Was it based on a religious perspective? I mean, at one stage, maps of the world had Rome in the middle because everything went back to Rome. That could have been a political, a historical, religious point. And then sometimes people's egos just got in the way. If you look at the picture on the right, you'll see a very interesting concept of when we look at America and we look at China and Russia and some of these countries, we sometimes say, wow, but Africa, it's big, it's a big continent, but actually America, Canada, and a couple of others are much bigger. That's not the case. That is a function of the Mercator projection that we've all got very used to. And Mercator was defined to assist in navigation across the world and across the oceans. And the whole idea was to, as it says there in that second point, a straight line will represent a standardized heading. So if you were sailing from one place to the other and you knew it was at 37 degrees, you could sail that line and you'd get to where you wanted to be. But it did have some very strange distortions in it. And one of those distortions is that the northern latitudes and the southern latitudes are overrepresented. So if you look at this map of the world, which is a Mercator map, you look at Greenland and the size of Greenland, so the big white continent between Europe and Canada, and you look at the size of America and Canada, etc. And I'm going to use a couple of examples here. So we talk, and just want to touch on here, we have our equator in horizontal, and we have our Greenwich or our prime meridian in the vertical. And then some interesting things. You might have heard of the term called the null island. And the null island is at 0.0, and many times when we're working with GIS data, we get data where one of the coordinates is 0.0, and we call it the null island. So the data is captured in the null island. And some other you might have heard of the term called Point Nemo. Point Nemo is that point which is on the right of the picture, left of the picture now, and it's somewhere in the Pacific Ocean. And that's the point in the Pacific Ocean which is the furthest away from any continent. So in east, west, north, south is away. But let's look at another picture here, and this is one which shows the actual size of Antarctica. So when you look at this slide, Antarctica looks quite big. But when you look at it, when we do an Antarctica-centered projection, it's actually not the biggest continent. It's not very big at all. But because of our Mercator projection, we typically overrepresent the size. So I know this is small and maybe difficult for people to see, but this is illustrating the different sizes of the countries. And here you start seeing Antarctica is the second biggest. Greenland will not even feature on this because Greenland is not actually that big. Or there you can see it, sorry, third line, second from the left. But South Africa is over there. And so in the bigger scheme of things, we have one of the bigger countries. And that's just because we do not get overrepresented on a Mercator map because we're in very low latitudes. We're not in very high latitudes. And these are all the other countries and how they get smaller. But let's just look at Greenland specifically. So on the right of that picture, you see Greenland on a Mercator map, but on different maps, the size gets more in line with what it actually is. And just note that when you use the wrong projection, you might distort the size, the shape, etc. And it all depends on what you're trying to do, what you're trying to map, and as I said earlier, the extent of where your mapping is. If we look at this concept of the properties of a projection, projections can potentially maintain one or two of the parameters or properties, but they can't do more than that because it's all the models have limitations. So we have things like distance, direction, shape, area, and scale. Your scale can be distorted depending on where you're mapping and what projection you're seeing. So no projection can preserve all these properties. And I want to give you an example of this. I took 4 well-known projections in South Africa. Transverse Mercator, which is our Gauss, or South-Orientated Transverse Mercator, UTM, Lambert's Conformal, and Albers Equal Area. And I also used Web Mercator, which is becoming more and more useful. And then Geographic. Okay, we can't measure distance in that, so we can't do that. But these are some of the projections we typically use, and we'll get back to these in more detail. But look at this. This is a road in Gqeberha, along Summer Strand. And here we took a piece of road and we mapped it, and I reprojected into different projections, and I calculated the length. Now, if you look at the first 4, it's sort of the same, give and take. But look at Web Mercator. We are out by a factor of nearly 0.9 of a kilometer. So Web Mercator works really well for visualization, especially across a globe, but be very concerned or aware of the limitations on when you're calculating areas or doing a modeling or analysis, because you are going to over or underrepresent. So the same thing if we look at direction. Here, all of them within 1 degree, 2 degrees of each other. So give and take, there is some differences, but not too different. But look at area. If we look at area here and we look at the top 4, 772, around there, and Web Mercator is over 1,000 hectares. Once again, Web Mercator can be used for visualization, but be very careful of using it for any analysis, calculating of areas, etc. And then I had some fun. I was trying to see if I could represent all of these projections in terms of shape. and I created a little man or a little face in WGS on the top left, and then when I reproject, you can see the face gets narrower and the mouth looks slightly different. But it doesn't actually show that much, so I found a picture which illustrates a shape of an aeroplane, and if you did different projections, how narrower, how longer the wings get, how longer the fuselage gets as you look at this. It just shows you how shape can be deformed by a projection. So be circumspect, be careful of what projections you use, because you could be adding some errors into the data if you're not using the right one. So take home message here. Each projection has a property it maintains, and it potentially could maintain more than one property. Area, distance, direction, shape, and the scale. Scales may be less important nowadays because we don't print out maps. We don't have fixed scale maps. We typically use digital maps. But still, be aware of that. And understand these limitations, understand the properties of the given projections, and use it with discretion. Because it is important, and going back to what I said earlier, we have standard projections, we have standard datums that we should be using, and you will be held to task if you're not using the right one for an area. Last section of this video is about the reversibility of projections. So can I take a projection and go from LO to Albers and then back to LO, and am I going to lose something? Is it reversible? So in the case of vector data, yes, it is reversible, because we're actually working with the coordinates and we rebuild the topology based on nodes and vertices, etc., etc. But when you start working with raster, you need to be careful, because here you resample the pixels every time you do a projection, and those pixel values will slowly change. And what I've tried to do in this example here is illustrate this. So what you see as the red line is a subplace boundary, or a suburb boundary, if you'd like to call it that. And what I've put in the background is a rasterized version of those subplaces. So here you can see, and on the right I give you an explanation. This data is in Transverse Mercator 29 Harderbeshoek. So it's in its correct projection, it's in its correct coordinate system, and you can see the line within a pixel follows the underlying raster. Let us move that one projection now to a geographic coordinate system, so not CGS, GSC. And here you can see that slowly the line in the top section has started to move away, because in that reprojection process, in the resampling of the raster, there's a slight difference. Let me go one step further and convert that and reproject it to Albers, and then just take it to the last one, where I take it back to Transverse Mercator. And here you'll see that boundary is not following the vector version of the same boundary, because you've resampled that data over and over again, and every time you're doing that resample, it's bringing in a slight error. So reversibility, projections can be reversed when they are in a vector file, but when you're in raster, you need to be very careful what you're doing and be very aware of how the data was created, what projection system the data was created in, and how you can use it. So a take-home message here: vector data can be moved backwards and forwards without problems. Raster data, there is an issue. And also that there's a difference between when you want to visualize data versus when you're wanting to do some analysis and modeling, where you need to just think about it before you go down that path. In the second part of the webinar, I've highlighted the different approximations of the globe and how we work with them and transform between them. I have then discussed the concept of projections, their history, and their various properties. These properties are important when deciding on a projection to be used for mapping or modeling. I've highlighted the concerns when moving between projections and how we can mitigate against this. In the third part of the webinar, I'll focus on the different types of projections, and I will highlight the common South African projections and when they should be used.